Griffiths E&M section 3.4.2, the monopole and dipole terms of the multipole expansion. In the last video, we wrote down that you could find the potential at every point in space if you took this infinite sum that told us, well, that related where I was looking, right? That's my r vector there, and where all the charges were, r prime to the n, my Legendre polynomials of the angle between those two vectors, and where the charges are integrated over that whole space. That's the multipole expansion. The exact potential is all of those terms, but the approximate potential is usually just the biggest term, right? And because additional terms accumulate, r squares in the denominator, usually the first term that's not zero is the biggest. Okay. So let's go ahead and explore those terms. So for n equals 0, we have what we call the monopole potential. I'll go ahead and plug in what all those are. So n equals 0 here, that's just 1 over r. I'm taking the integral of r prime to the 0, which is 1. My first Legendre polynomial is just 1 times the charge density integrated over all space. Well, 1 times 1 is 1. That doesn't matter. I'm integrating over all the charges, which is the total charge. 1 over 4 pi epsilon naught, 1 over r times the total charge. So that's the monopole term, and that's something I feel like we're familiar with intuitively because we've looked at potentials from single charges that have charge q. The next term, which usually dominates when the monopole term is 0, is called the dipole term. I'm going to go ahead and plug in n equals 1 to my top expression. I get 1 over r squared. I've explored this a little bit in a previous video. Taking the integral of r prime. My first Legendre polynomial is just the argument, so cosine alpha. Integral still has that charge density in it and the volume. Okay, so this is the dipole term. This doesn't look at all like what we saw previously. So let's go ahead and explore what r and r prime are representing again. See if we can simplify it. Okay, so I have some origin. I want to find the potential at a point in space P. That vector, by definition, is r. I need to integrate over all of my charges. So here's a chunk that lives at r prime, and then the vector between those would be script r, but we don't need that right now, so I won't drop it. Okay. I can go ahead and write the dot product of these two vectors, just the definition. R dotted with r prime is r prime, and the angle between them is I forgot to write that, but that's alpha. Right, that's the argument in this cosine. Okay, dot product becomes r prime cosine alpha, and I'm going to go ahead and divide each side by the magnitude of my vector r. Okay, so I divide each side by an r. I'm left with an r prime over r times an, leave that out there, r vector over r magnitude time dotted with r prime. That's equal to r prime cosine alpha. Again, you can see what I'm doing here. This is going to match my argument inside of my integral. But r vector over r magnitude is just r hat. So I can go ahead and plug that into my expression here. 1 over 4 pi epsilon naught, 1 over r squared, and this is the integral of r hat dotted with r prime, but the r hat doesn't care about the prime coordinates, so that can come out of the integral, and I'm left with r prime integrating my charges over where they live. Okay, so how does that help us so far? If you look back or remember your mechanics class, we defined something called the moment of inertia. Okay, the moment of inertia basically said, I have some object, and what I want to do is I want to calculate the moment of inertia by adding up all of the masses that exist, and I want to weight those masses by the square of where they live. Okay. So I'm doing this weighted sum to find the moment of inertia. That's essentially what we're going to do here. What I have in this expression is I have the position of my charges, and I have the weighting, all right, the density, the mass, or whatever, and I need to add all those up through this integral. So what I'm defining here is a moment. It is not a moment of inertia, but it is a dipole moment. Okay, I'll call P the integral of r prime rho d tau prime. That's the moment of inertia. Oh, that was Freudian slip. That's the dipole moment. If I know where those charges are and I know how many charges I have, I can calculate the dipole moment of my continuous charge distribution. So then I can rewrite my dipole potential in a nice closed form, 1 over 4 pi epsilon naught, r squared on the bottom, and I'm going to dot, order doesn't matter for my dot product, r dot, p dot r hat. And that's my potential for my dipole. If you know where the charges are located, you can calculate what the dipole moment is, and you can dot that dipole moment with the direction that you want to evaluate your field in, and that gives you your dipole